Bismillahirrahmanirrahim. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Alhamdulillah, today I'm going to present proposal in geotechnical engineering. My name is Ahmad Hakimi Mat Nor. My supervisor is Prof. Madya, Dr. Saiful Azhar bin Ahmad Tajuddin, co-supervisor Dr. Faizal bin Pakir. So this is the title of proposal: Physico-Chemical and Engineering Behavior of Combination of Biomass Silica and Sodium Silicate Stabilized Butterfly Soft Clay. This is outline of presentations. Okay, start from introduction until planning of study. So for the introductions, over the 7 past year, residential and commercial developments have increased in Batu Pahat. This development was constructed on soft soil. Construction of roadway over soft subgrade is one of the common problem for road constructions. The usual approach for this problem is to replace the soft soil with the new material that suitable engineering properties. This is very high cost to replace that. So that's why the highway agency company is looking about the evaluate alternative method to solve to how to solve the to construct the highway on the soft subgrade. The method can be achieved in two ways, namely in situ stabilization and also ex situ stabilization. Actually, the soil properties that has been modified can modify the properties of the soil by using technologies, as well as when we know the existing result of the soil. Okay, for the problem statements, actually the soil stabilizer is categorized by two. First is traditional, and second is non-traditional. For the traditional additive include cement, lime, fly ash, and bitumen material. While for the non-traditional additive consists of various combinations such as enzyme, liquid polymer, resins, acids, silicate, ions, lignin, and lignin derivative. For the traditional soil stabilizations, material like cement was widely used for ground improvements on the various projects that have led to accelerating the production of ordinary Portland cements. It has proved that release huge amount of the greenhouse gases like carbon dioxide (CO2) into the atmosphere. We can imagine to produce 1 ton of the ordinary Portland cement is approximately equivalent to releasing 1 ton of the carbon dioxide (CO2) into the air. SECNEC 2018. Why we use for the non-traditional stabilizer? This is quite economical and sustainable, and also environmental friendly. Okay. So nowadays, non-traditional stabilizer like powder and liquid probate stabilizer has been used in Malaysia to stabilize soil, and knowledge is likely limited to the global performance of the treated grounds. However, no comprehensive study has been carried out to understand the fundamental of physical, chemical, and microstructure behavior of such treated clay of both stabilizer and their influence on the observed engineering behavior. Is it conclude that there is a need to study the physical, chemical, as well as microstructure behavior of probate stabilizer treated butterfly soft clay, and use them to explain some aspect of the observed engineering behavior in a well-controlled laboratory condition first, before extending into the field condition. So this is for the research question: why combine biomass silica and sodium silicate as a stabilizer material? From the systematic literature review, the result from a keyword is about 50 articles were found, and then after process screening and eligibility was performed, so only 12 articles are included and related to this research. This means the researcher use same stabilizer, which is the TX-85 and also SH-85, only 12. This is from platform Scopus platform. Okay, so from here, most of the researcher is interest with laterite salt, study about the laterite salt, and the second is marine clay. Why for the clay back material, green bentonite and white colonite is little researcher study about that area. Okay, from figure 1.2, the number of application and type of stabilizer in terms of stabilizing by using TX-85 and SH-85. So there is no researcher study about the combination between both of the stabilizer, which is of SH-85 and TX-85. So that's why I use the combination between biomass silica and sodium silicate. So according to the SECNET to 2018, both material of stabilizer, which is the combination between calcium based stabilizer and sodium silicate, there is no problem to mix together, and no implication from mixings why both stabilizer can implement each other. So this is for the research gap. Okay, first, a combination of two material of the stabilizer in order to treat of soft clay, of the butterpart soft clay. This is for about the combination is clear because of the research question was answered that combination. And then second is physical-chemical behavior and engineering properties on butterpart soft clay treated with biomass silica and sodium silicate. So the gap is in terms of the area and also type of the soil. So this is that chemical treated butterpart soft clay. This is the gap lah between the other researcher. And then the third is cyclic loading behavior of butterpart soft clay treated with biomass silica and sodium silicate. So for the cyclic loading, according to the figure 1.3 here, show there is no or 2 liter of the previous researcher use a cyclic loading test to investigate the cyclic loading effect on soil treated with chemical stabilizer. So here the highest test is UCT. UCT compulsory test to investigate the in terms of the strength of the salt and to investigate the what we call that the best proportion, the optimum proportion of the stabilizer. Okay, so this is the objective of the study. First, to characterize the butterpart soft clay and combination of selective additive, which is biomass silica and sodium silicate, through the physical-chemical and macrostructure behavior. And then the second is to determine the changes in engineering properties of treated butterpart soft clay with various percentage of selected combination additive at different curing periods. And then the last one is to determine the performance of combination of both stabilizer treated butterpart soft clay as the foundation for strict footing in laboratory physical model and numerical modeling by using Plexis software. This is scope and limitations of the research. Okay, we start from the preparation of the sample. The sample will be taken at the depth 1 meter to 1.5 meter, and then the stabilizer will be obtained at the Probes company, which is SH-85 and TX-85, and then we can mix by using designation of the stabilizer and then we can investigate the engineering behavior by using testing like turbid limit silase compaction. This is for the properties of the soil. And then UCT to investigate the shear strength, and then CBR to investigate the bearing capacity, and then consolidation to investigate the compressibility behavior, and then for the consolidated undrained cyclic reservoir for investigate the cyclic load effect on the cyclic loading. Okay, while for the physical, chemical and macrostructure behavior, the testing involved is XRD and SRF. Okay, SRD, SRF actually to determine the mineralogy of the soil, and soil was treated by using probe stabilizer, and then SCM, and then FTIR. Okay, FTIR actually to determine the what we call that flocculations reaction, and then TGA to determine the Fazolinet reaction, because of the thermal. When the Fazolinet reaction occur, they can produce the heat, and then pH to determine the exchange reaction, cation exchange reaction. Okay, so after physical chemical, we go to the physical model, and then check with the numerical modeling practice, and then finish. Okay, the significance of the study first, to identify the possibilities of using combination of biomass silica and sodium silicate to stabilize batu pahat soft clay, and then a detailed study of physical, chemical and macrostructure are necessary to understand the mechanism involved in chemical stabilization. Is it unclear whether and then the last one is it unclear whether the negative impact of batu pahat soft clay on combination of biomass silica and sodium silicate stabilized is due to inhibition of Fazolinet reaction product formation or inhibition of its cementation activity? Okay, so we go to the literature review. Start with soft clay. As you know, clay is the expensive soil that can be found across the globe. They are likely to swell and shrink due to high clay mineral like mormonite, expandable illite, and vermiculite. This characteristic causes any structure and infrastructure built on clay soil area, for example, roadway, building, bridge, and other civil engineering structure, experience numerous costly damage. Clay soil are very high compressibility and low compressive strength, and then compressive failure and massive settlement that cause major damage to building, foundation, roadway on the clay soil are due to their low bearing capacity. Okay, according to the Terzaghi and Peck 1967 state that very soft clay have very low shear strength, which is less than 25 kPa, for the very soft clay, and then for the soft clay between 25 to 50 kPa. This is the strength, the shear strength of the very soft and soft clay. Okay, for the biomass silica is the soil stabilizer product which is calcium based stabilizer such as hydrated lime, Portland cement, and etc. So table 2.4 show the chemical composition of calcium based stabilizer. This is for the biomass silica chemical composition, and then this is for the Portland cements, and then this is for hydrated lime. Okay, for this study we use the biomass silica. So calcium hydroxide CO2 is a major chemical composition on this stabilizer. In the presence of water, the calcium ion released from this stabilizer reduce the thicknesses of double diffuse layer through cation exchange and flocculations, agglomeration reaction. This is primarily responsible for improved in walkability through reduction of absorbed water and decrease in plasticity index. In long term effect, the pozolanate will be occur between the calcium ion of the stabilizer and silica and alumina of the clay mineral, resulting in the formation of cementitious products such as calcium silicate hydroxide, calcium aluminate hydroxide, and also calcium aluminium silicate hydroxide. This is what we call it pozolanate reactions. So for the sodium silicate, actually sodium silicate is the non-traditional chemical stabilizer. This is for water-based stabilizer. Okay, the function of this stabilizer is to improve the construction material and enhance many of the engineering properties of the salt. In addition, also can reduce swell. Okay, this stabilizer can reduce the swelling and then bind particle of the salt at the same time, fill the void between particles. This is the function of the sodium silicate, TX-85. Mechanism, in terms of the mechanism of reaction, usually from this stabilizer, usually cation exchange and also flocculations will be occur by using this stabilizer. Okay, go to the mechanism of the stabilizations. So this is for the cation exchange. Okay, the cation exchange. In clay, exchangeable cation like calcium, magnesium, sodium, and potassium are tightly detained by negatively charged clay particles. Okay, basically the salt is negative charge, and then calcium, magnesium, sodium, and potassium is positive charge. When the positive and negative, there will be react, and then the salt will be natural. Positive and negative will be natural. So this is what we call the cation exchange. Okay, so from the cation exchange, the reduced spacing after ion exchange and increase age of the water layer. So the water layer will be reduced. That means the water will be flow out, and then the salt will be strengthened. Okay, so the type of the observed cation depend on the environmental conditions such as the temperature and pH. pH is very important because the highest pH, the highest what we call it cation exchange capacity will be occur. And the chemical and biological content of the water in the pore space. Okay, via cation exchange, the structure of clay particles might not be altered, yet a significant modification in the physical and physico-chemical properties of the salt can occur as a result of the exchange process. Okay, this is for the flocculation and agglomeration mechanism of salt stabilization. Okay, this is the process of the flocculation begin with cation exchange. Okay, flocculation is a process where particles contact in the solution and adhere each other to form flakes of flock or clump of clay, steel, or sand particle in salt matrix. The flocculation process transfer the clay microstructure from a more aligned, this is the without this is unstable clay material. The structure of the clay is quite aligned orientation. After process of the flocculation, the particles of the salt will be random orientation. Okay, this is for the pozolanate reaction. Okay, pozolanate reactions. The nature of the reaction that occur tends to form strong bond between the particles in the matrix over time. a stabilization process which happen over an expanded period, which is affected by chemical and mineralogical compositions of the soil and temperature simultaneous. So this phosphorylated reaction will be take time, okay, to react, to form the soil. Okay, this is the chemical equation for the phosphorylated reaction. So this is calcium plus OH, and then plus the soluble clear silica. They're going to be calcium silicate hydroxide. Okay, and then calcium plus OH plus soluble clear alumina, you're going to be calcium aluminium hydroxide. So this is the how the phosphorylated reaction will be occur. So this is the black one. The black one is the clay particles, okay, bond by the cementation material from phosphorylated reactions process. So the clay particle will be bound with cementations, okay, material. This is from cement, okay, cement stabilizer, and then this is from the calcium base calcium hydroxide. So the clay particle will be bound with the calcium silicate hydroxide. Okay, go to the methodology of research. The experimental program is drawn up with the main focus to evaluate the physico-chemical as well as microstructure and engineering properties of treated and untreated butterfly soft clay. Second, to evaluate the physico-chemical as well as microstructure properties, various types of the laboratory experiment will be performed, namely pH measurements, SRF, SRD, SEM, FTIR, and TGA analysis. For the engineering properties like attribute limit, particle size analysis, okay, SILAS, UCT, okay, consolidation, CBR test, and also consolidated undrained cyclic tracer test will be performed. And then the physical box test with large scale will be with small scale. Small scale will be carried out based on the optimum stabilizer content and curing periods. Okay, this is flowchart of methodology. Okay, we start with the material characterizations for the butterfly soft clay, and then this is for the stabilizer. For the TX-85, we only check chemical properties, pH only, because of this is liquid stabilizer, okay, water base. And then this is a powder. This is the calcium base, so we can check the chemical properties by using pH and TGA, and also we can check the mineralogical by using SRD, SRF, and also FTIR. And then we can check the particle size distribution and specific gravity for this stabilizer. Okay, for the butterfly soft clay, we need to check the physical properties by using particle size distribution, attribute limit, specific gravity, moisture content, compaction. And then we need to check also for the chemical properties by using pH and TGA. And then for the mineralogy, okay, by using SRD, SRF, SEM, and FTIR. This is for the strength properties by using UCT and also odometer consolidation. Okay, after we check the characteristics of the soil and stabilizer, we go to the remolded sample. Okay, prepare the remolded sample, mixing with the stabilizer, so and then cure at the temperature 27 plus minus 5 Celsius. And then for the curing, depend on the type of the test. Okay, okay, for the physical properties, okay, we can use UCT, okay, odometer test, CBR, consolidated undrained cyclic tracer test. Okay, for the chemical properties, we use pH and also TGA. Okay, pH actually to investigate the cation exchange. Okay, and then this is to investigate the pozzolanic reaction. Okay, and then this is what for the mineralogy test, we use the SRD, SRF, FTIR, and SEM. FTIR we can use to check the what we call it, to determine the flocculations reaction. Okay, so and then after perform the physical properties, we can prepare the physical model and numerical modeling by using Plexis, and then data analysis and discussion, and then conclusion and recommendation, and then finish. Okay, this is table 3.1, list of the tests for investigate the engineering behavior. Okay, this is standard reference. Basically, we use British Standard and also ASTM. Okay, table 3.2, list of tests for investigate the physico-chemical and mineralogy behavior. Right. Okay, this is stabilizer combination scheme for stabilized soil. Okay, this is designations. Okay, designations. So L equal to liquid, P equal to powder. P stand for powder. So L 0%, P 0%. That's mean untreated. Untreated. That's mean 100% of the button parts of clay, 0% liquid stabilizer, 0% powder stabilizer, and then 3% liquid, 0% powder. Okay. So button parts of clay going to be 97, and then TX-85 3%, and then SH-85 going to be 0%. Okay. So until L3, P 15. Okay. So okay, so for the liquid we constant use 3%, and then for the powder start from 3 until 15%. Okay, this is table for laboratory testing program for engineering properties. So start from a tebit limit. Okay, this is the stabilizer content, start from untreated to L3, P15. Okay, there is no curing time here. And then also okay, for the compaction test we use only untreated soil only. Okay, from here we can use this parameter like the what we call that optimum moisture content and maximum dry density to mix the sample. And then UCT to investigate the strength and also to determine the best proportion, proportion of the stabilizer. So for here, from here we use curing time until 19 days. Alright, and then this is for the California Barrier Ratio, CBR, for soup and unsoup. Okay, and then this is for the odometer consolidations. Alright. Okay, for the odometer consolidation, the stabilizer content start from untreated, and then L3 plus P6, L3 plus P9, and L3 plus P12. Okay, this is for the curing time. Okay, for the consolidated undrained cyclic tracer test, this is what we call the advanced testing. We only use for the optimum percentage, optimum percentage determined by UCT. UCT, from UCT, result from UCT we can know the best of the proportion. Okay, also for the physical test we mix with the optimum percentage. Okay. Okay, this is for the testing program for odometer consolidation test. So there is a series of load and unload stress. Start from 25, 50, 100, 200, 400 and 800, and then unload to 400 and 200. Okay, this is for 0 days curing, 7, 15 and 28, 14 and 28. This is number of the sample. Okay, this is for the testing program for consolidated undrained cyclic treasure test. Okay, the consolidated undrained cyclic treasure test will be applied according to the different frequency, different confining pressure, and different cyclic stress, as so in table 3.7. Okay. The frequency start from 0.5 to 2 will apply to simulate the cyclic loading during wind action, earthquake, and also for the traffic loading. Okay, so this table for the laboratory testing program for physical, chemical, and microstructure properties. This is for the SILAS. Okay, this is for pH. Okay, SRD, SRF, SRD, FTIR, SEM, and TGA. This is we can compare untreated and with optimum percentage only. Okay. Okay, while for the pH we can do it all for all percentage, and also for the SILAS test. Okay, for the physical model test, actually the purpose of the physical modeling, first to study the effect of different depth of clay subgrade treated with a combination of biomass silica and sodium silicate, and then to investigate failure mechanism of treated bottom parts of clay. Okay. The measurement for penetration of rigid foundation will be measured by transducer. Okay, this is for rigid foundation. This is the width is about 75 mm. Okay, this penetration of the rigid footing will be measured by transducer, and then deformation. Okay, deformation of the soil will be measured by photographically as the displacement of the footing increase. Okay, load on the rigid footing will be applied by a load cell, and at the same time the load data will automatically record by using data logger with connected the computer. Okay, the load will be applied by using load cell. Okay, load cell here. Okay, this is treated layer with different depth D. Okay, this is for the plastic layer as a buffer zones to separate between treated and untreated. This is untreated layer. Okay, this is the box with size 100 mm multiply 600 and 300. Okay, this is outlet flow. Okay, to flow out the water during what we call that curing time is about 7 days. Okay, the sample of untreated will be prepared by dry salt in the oven, and the salt will crush by rubber mallet and sieve for 4 mm size. After that, the salt will be mixed with water according to nature moisture content. Okay, for the untreated salt we can mix with the nature moisture content, while for the treated salt will be prepared according to the optimum percentage stabilizer and optimum moisture content. Okay, before start the test, salt in the box should be applied a certain load to achieve the current pressure as designed in the table 311 for 7 days. Okay, the process is to make sure the sample is saturated over consolidated condition before starting the test. After the during period passes and 50 mm depth of the treated layer was prepared, the rigid footing can start apply load to drive into the soil layer. The maximum penetration is about 100 mm, Then the same procedure will be repeated for another step, which is for 75 mm and 100 mm. So this is table 311 about the testing program for physical model test. Okay, this is the current pressure. Okay, only to type the current pressure. First 6 kPa and then 14 kPa. Okay, this is a different depth of the treated layer, 50, 75 and 100. Okay, this is curing time. This is the penetration of the footing. Here the maximum of penetration is about 100 mm. Okay, but for the analysis, we only analysis for 25 mm and 50 mm only. Okay, and then we go to the numerical modeling by using plexis. Actually, the purpose of the numerical modeling is to allow a more detailed investigation of the problem and also to verify and compare the result from physical model. This is because by using plexis software, the parameter of solve may easily be varied and detail of stresses and deformation throughout the system may be studied. Okay, go to the expected outcome. Okay, first, the characterize of physical, chemical and microstructure batu-batu soft clay and selective additive, which is biomass silica and sodium silicate, can be classified. And then a strength, geochemical and macrostructure properties for stabilization of batu-batu soft clay solved by using combination of biomass silica and sodium silicate can be classified. The last one is a strength prediction through the physical modeling and numerical modeling for stabilization of BPSC by using a combination of biomass silica and sodium silicate can be established. Okay, for the conclusion, okay, this study will assess the knowledge about physical, chemical as well as microstructure behavior of probe stabilizer treated batu-batu soft clay and use them to explain some aspect of the observed engineering behavior in a well-controlled laboratory condition first before extend into the field condition, especially in terms of cyclic loading effect. So this is reference, okay, that related with my study. Okay, this is planning of study. Okay, start. Okay, so that's all. Thank you. So wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh.